Suppose we are asked to find y double prime, that is the second derivative of y with respect to x, if the square root of x plus the square root of y is equal to 1. Now, in this case, y only shows up once, and it's actually not too hard to solve for it, right? Just a couple steps of algebra, and you can write y as a function of x. And you can simplify that a little bit and take the first and second derivative pretty readily to get this without too much work. I recommend you try that to check our results and confirm that what we do here actually does give us the same answers. In this case, that would be easier than using implicit differentiation. But let's use this as a simple toy problem to kind of play around with some things and see how we would apply implicit differentiation to a problem like this, so that if you ever have to apply it to a more complicated equation, you have some idea of how we would do that. So let's begin by, well, let's write this in a way that makes it easier to differentiate. So we'll go ahead and write the radicals in exponent form. So we have x to the 1/2 plus y to the 1/2 equals 1. And let's go ahead and differentiate both sides. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. The derivative of y to the 1/2 is 1/2 y to the negative 1/2 times the derivative of y. Right? Again, we have to be careful, watch out for that sneaky chain rule here. Y is a function of x. We are differentiating with respect to x, so we need to write that carefully. This is another reason why, if you're not too comfortable with things yet, maybe don't use the prime notation. You could stick with Leibniz notation, d by dx. That's a little bit more explicit, and it reminds you, every time you write it, it reminds you what variable you're differentiating with respect to. Because it's not always x, right? If your variable is t, you could have a d by dt, and that's what you're differentiating with respect to. You could take x as a function of y and look for dx by dy. There are a couple of exercises in the textbook that talk about that. You could try those. It can be a little bit brain-bending at first. But anyhow, the derivative of 1 is 0, no matter what variable we're differentiating with respect to. Derivative of a constant is always constant, or always 0. So we have that. Let's start clearing a few things out here to simplify this equation. Let's multiply both sides by 2, so that we'll get rid of the halves. 0 times 2 is still 0, so that's fine. And we have this one term here with y prime. So we have y to the negative half times y prime is equal to negative x to the negative 1/2. And to get rid of this, we could divide both sides by y to the negative 1/2. And I'll go ahead and write it that way at first, but there's a simpler way to do this. Instead of dividing by y to the negative 1/2, we could multiply by both sides by y to the positive 1/2, because that would give us 1 on the left when we multiplied, and on the right we would then have y to the 1/2. You can also see if you do the division, we have this negative power in the denominator. We can bring that up into the numerator, and we get an expression that looks like that. Which, if we want, we could go back. The original equation was given to us in terms of radicals, not fractional powers. So if we wanted to write this in terms of radicals, we could do that, and we could say that this is negative square root of y divided by square root of x, just translating those negative and fractional exponents back into radicals and fractions. So there's an expression for y prime, right? We wanted y double prime, so let's differentiate this again. We could use this radical form and use the quotient rule, but let's not. We have this nice form right here. Just a little bit of product rule there. So we have the derivative of the first factor, x to the negative 1/2. That is negative 1/2 x to the negative 3/2. y to the 1/2. Minus, this is minus instead of plus because of this negative up front. I didn't want to write an extra set of brackets. Be careful with signs and grouping. X to the negative 1/2 times, now we take the derivative of y to the 1/2. That is 1/2 y to the negative 1/2, again, times y prime. Right, just like we did earlier. So, cleaning this up a little bit, we have positive 1/2, x to the negative 3/2, y to the 1/2, minus 1/2, x to the negative 1/2, y to the negative 1/2, times y prime. But y prime is this thing right here. That is negative x to the negative 1/2, y to the 1/2. And I'll do this to help you see what's going on here, right? We have y prime. Y prime is equal to this, so I'm just plugging that in. So let's continue simplifying and cleaning things up a bit. We have a negative here times that negative gives, it's going to turn that into a plus. We have 1/2. X to the negative 1/2 times x to the negative 1/2 is x to the negative first. Y to the negative 1/2 times y to the positive 1/2 is y to the 0, which is 1. So that all simplifies down to this. And let's see, if we clean this up a little bit, we can pull out the 1/2, and the lowest power on x is negative 3/2. And when we factor those out, we're left with y to the 1/2 here. And we've gotten the 1/2 out, and that leaves an x to the 1/2. Let me factor that. Okay. So you could leave it, like the previous expression or like this one, but again, we were given an equation using radicals, so let's rewrite this back in radical form. The 1/2 and this negative 3/2, those represent reciprocals that'll go down in the denominator. The numerator, y to the 1/2 plus x to the 1/2, that is square root of y plus the square root of x, which you should probably write the other way around with the x first. Doesn't really matter too much, though. And we have 2 times x to the 3/2. X to the 3/2, of course, is x radical x. So we have this. So that looks like our y double prime. Except, just as we did here when taking this derivative and we got this y prime here, we don't want to be stuck with a y prime. We look for ways to simplify things. We know what y prime is, so we can substitute that in and simplify. Well, we have square root of y plus square root of x divided by 2x radical x. But the square root of x plus the square root of y is equal to 1. At every point on this curve, that is true. And that means that this numerator can just be replaced with 1. And this is y double prime. Let's follow the chain of equality back. We have these equal signs here. This is transitive, so it's saying that these are all equal to, following that back to the first thing I wrote in that line was y double prime. We have y double prime is equal to this stuff. It's not necessary, but if there's a long chain of equality, we will sometimes copy that thing back down here to put it on one line. You could do that if you want. Could be handy. But yeah, so we have y double prime is equal to 1 over 2x radical x. Or if we wanted to write that a little bit more compactly, and we don't mind some weird exponents, that is 2x to the negative 3/2 power. Now again, in this particular case, it is a little bit easier to not use implicit differentiation. If you solve for y first and clean it up, then you can take the two derivatives directly pretty quickly. I recommend you do that. Make sure you get the same result. Oh, I'm sorry, that is not 2 there. That is a 1/2, isn't it? I was getting a little bit too... Right, because this 2 is in the denominator, so we have a 1/2, but then the x to the negative 3/2 comes out separately. There we go. But yeah, you can try taking the derivative, make sure you get something like this as a result, It is faster to do it directly. But again, here are some more examples of working with implicit differentiation and how we can manipulate that and making use of previous information to simplify what we get as we go.